This is Iceberg for data engineers. You guys can see the slides and not the big Zoom thing I have hovering over them, right?
Yes.
Okay, good. Thank you. All right, so Iceberg for data engineers. First off, I want to just, I'm not sure what this group's background is exactly, but I want to talk a little bit about what is Iceberg and sort of what are table formats in general, just to orient us to what we're going to be discussing today. So what is Iceberg? Iceberg is a table format. and it might not be obvious what a table format is. So let's think about that just a little bit. A table format is sort of like a file format, only instead of keeping track of individual rows, it keeps track of what files are actually in a table. So we think of tables, the Hive table format is kind of the canonical example where it's made up of all the files in directories under a certain location. Typically that's oversimplifying, but let's go with it. So that's keeping track of, the files that make up some data set. And we're talking about really large data sets, and that's why we have to talk about hundreds, thousands, millions of files. But the thing that I want to point out is that just like file formats, not all table formats are equal or have equal capabilities. So just like with a Parquet-like columnar file format, you do certain things in order to get different properties or guarantees out of it. So with Parquet, for example, you organize data by columns, and then you keep track of offsets and statistics about those columns in order to be able to sort through them really quickly. Be able to skip as many columns or as many rows as possible in that format. A table format is the same thing, only the idea is not skipping chunks of data or a chunk of values in a column. The idea is actually skipping through the files themselves. Which files in a table do we need to read or not read? So Hive, again, you just found a whole bunch of directories and said, these three directories are the ones that we need to read for a query. You only read the files in those directories and then you moved on. But the problem with Hive was that you got no transactional guarantees whatsoever because you were selecting directories and you couldn't make files appear in a file system at exactly the same time. There's no transactional guarantees in a file system at that level. And so we lacked transactional guarantees in our tables, which it turns out is a huge problem for things that act and look like databases. The other thing to keep in mind here is that just like columnar file formats, there are performance trade-offs to decisions that you make at this level. So formats like Delta Lake and Hive don't keep statistics or extra information about each column in a particular file. And so you can't skip through the columns, through files based on the column stats that you have. If you don't keep column stats, you can't say this file doesn't match because its stats are outside the range of what I'm looking for. So that's what a table format is. Iceberg, we think, solves all of those problems. Iceberg is also a standard, and we were talking about the spec just a minute ago, and that's one thing that I want to really highlight here. So it's not just a format, a way of doing things. It's actually written down as a spec and an open source library, and it's something that you can contribute to. It's something that you can shape the future of, and it is 100% open source and available. We think that that's really super important for table formats because a table format is something that ideally you want everyone to support, just like Hive. Everything supports Hive tables, and that's a really positive outcome because you can use Spark and Flink and Trino all on the same tables. Now, the trade-off there is that you have no transactions, so you can't do it safely. But we still want to share a table, share the data at rest across all these different database engines. So that's super important and something that we want. Again, to do that, we think it needs to be an open source standard. I just got a notification that everyone can see my application, so that's great. Anyway, we want this to be an open source standard, a well-documented spec, and something that is possible to integrate into multiple query engines. Not just the query engines that are around today, but whatever comes out tomorrow. So that's what Iceberg is. But the larger question is, why should you care about Iceberg? And that's really what I want to dig into more today than anything else. So the high level here is that Iceberg exists really to fix the productivity of data engineers, data analysts, data scientists, and basically anyone that is using data for a living. We built this at Netflix because we saw a need here. And frankly, we saw a lot of converging needs. We saw a lot of issues like, I can't trust when I write to this table, this is too slow and doesn't scale, or things like, wait, I renamed a column and wrote into this table and now everything is broken. Those are three different aspects of productivity. And so we can think of them as three separate areas. So Iceberg adds reliable transactions. It unlocks performance bottlenecks and really allows us to scale up to Netflix-sized data sets. And then the third thing is we're fixing usability. Now, I just gave a talk actually at Trino Summit last week about unlocking performance with Iceberg and Trino. We're not going to talk so much about unlocking performance today. How we do that is really more of a technical, deep technical thing. Go check out that talk if you want more on that. Likewise, reliable transactions. That's kind of the boring part of Iceberg. And I think what I talked about the last time I was addressing, the SF Big Analytics group. So today, what we're going to focus on is usability and really how usability affects your productivity. How do we make our data engineers more productive with those aspects? So let's get a little more concrete and talk about what does usability mean? Because I think without knowing what usability actually means or getting a little more concrete, we tend to think of it as features. Oh, does it have feature X or feature Y or something like that? And there's a lot to usability that doesn't have to do with features. Now, like I said, Iceberg has the features to make it performant, the features that meet your reliability needs and things like that. This is used in production in a lot of places, but today we're focusing on usability, and that means I get to rant about my fridge, which I'm going to jump into like a 5-minute rant about my fridge. So I hope everyone is with me on this one. This is, a study in usability. So let's talk about my fridge. This is my fridge. We put a name tag on my fridge to try and obscure the fact that my children's handprints are all over it. But it doesn't appear to have worked, at least at this large of an image in front of me. So, well, there's that fun. But let's talk about my fridge and usability. I don't think anyone ever thinks of their fridge in terms of how usable it is, which really goes to show how usable most fridges are. Right? If you're not thinking about something that you interact with daily and it just works, that is a good usability experience. So let's look at a couple of things that annoy me about my fridge and sort of draw some conclusions about usability from there. So first of all, my fridge has this nice little feature in the door where you can put a glass in the door and push it forward just a little bit, and the fridge dispenses into your glass a whole bunch of ice. And at that point, you're probably thinking, I would like some water to go along with this ice. And so you look at how to switch it over to water, and look, there's this nice large button that says water on it. And so you hit, without moving your glass, you hit the water button, and it immediately sprays water on your pants because water and ice come out of different locations in my fridge. And we actually have to warn people every time they come over to my house, including people that just haven't been there in a couple of weeks, that if you don't put your water glass in a different location after getting ice, well, it's going to spray water on your pants and the floor, and I'm going to laugh. But this is a terrible usability experience, right? Whose idea was it for ice and water to come out of completely different places? And not only that, the most unintuitive place for water to come out. It comes out right in front of the button that you can see here, and like well away from where you would normally set a glass. So even people that don't get ice first end up spraying water on their pants. It is hilariously awful. So what we can draw from this is, think about how people are going to use this, and think about how, think about the expectations someone is bringing to this system, and, don't surprise them in an unpleasant way. All right, so second usability lesson that we can learn from my fridge is that my fridge has two doors. Actually, sorry, it has a freezer door and it has a normal door, but it has a door within a door, as you can see here. So we've got this tiny little door that opens just to things that are actually in the larger door, which is kind of crazy. You can see it a little better in this one, where you've got, this is the tiny door is closed, the large door is open. So you can see a lot of space in the door and a tiny door. Now, the problem with this situation is not that it sprays water on your pants. I think fridges can only do that so much. The problem is that I'm constantly opening the wrong door. I needed cheese. Which one? And you open the fridge and you think, oh no, that was in the door. So you have to close it and reopen it with the other door. And not only that, it's even worse. There is a door into the door compartment, but it's only in the center. So like the very center shelf opens, and you can access things there from inside the main fridge, but otherwise you just have to close the fridge and open up the door. So this is just constantly confusing. And the lesson here is that it takes a ton of mental energy just to go to the fridge, open the door, and pick out what you were thinking of, right? You have to think, wait, is that in the inner door or the outer door? And it's actually surprisingly ridiculous how often I just get it wrong. So hopefully that was a sort of silly way to point out a couple of just very basic things about usability. So the first is avoid unpleasant surprises. No one wants water sprayed on their pants when they try to get a drink of water. It's just ridiculous. There's no need for this to happen. Think about what you're doing ahead of time and follow the principle of least surprise. Things should work the way people assume that they work. The second, I think, is slightly more subtle, which is that we don't want to steal attention away from people that are doing things. In general, this causes context switching. So I'm going from, hey, I need milk for my tea, to, wait, which section is what I want in, and I have to think about how to operate a fridge. Now, most people never think about how to operate a refrigerator. It's just kind of ridiculous. So those are the two things that I think we can take away from this. You shouldn't have unpleasant surprises. Things should just work as expected. And then after that, just get out of the way. Don't require anyone's attention more than necessary. And that's particularly important for data engineers. Data engineers have a lot going on, right? We expect them to know the customer's data model, what the customer wants, the data model of anything that other people are doing, to be able to join them. We want them to think about, how to do those joins or those combinations of data in efficient ways. There's a ton to think about here. And what we don't need is to surprise them with things like, hey, you just renamed something. Sorry, you can't do that. Now you've corrupted your table. And we also don't need to steal their attention and make them think, is this something that I can actually do? Right? How do I do this? We don't want to have people thinking about the table format all the time. I'm actually trying to convince you guys not to think about Iceberg all the time. So what we do is we try to make Iceberg as invisible as possible. And let me show you how. So first of all, I think the main failure of the Hadoop ecosystem for a very long time has been these usability things. You just could not be productive. And one of the main ways is that there are just a lot of paper cuts and issues that could take a day or a month of your time at any given time, just lurking in the background. So a couple of those things that we've fixed in Iceberg are the two that I want to highlight right here. First of all, schema evolution. You should be able to add, drop, rename, reorder, and I think there's a fifth. Update, so widen types, at will, right? We've had this capability in SQL tables for, well, more than 30 years. And so it's kind of ridiculous that in the SQL, Hadoop space, we don't have proper schema evolution. And proper schema evolution comes with a few, different things. It needs to be instantaneous. We don't want to go rewrite an entire table worth of data just to rename a column. That's not really true schema evolution. That's just a really expensive table rewrite that happens when you run a DDL statement. The next thing is that it needs to be safe. Using both ordinal-based and name-based schema or column resolution just doesn't yield the right result. So using name-based resolution, comes out of the box with Parquet, you end up getting situations where you can resurrect columns from the dead. And that's really, really bad, right? Because if you delete a column and then 2 years later, someone else adds a column with the same name, you don't need that data mixing, right? And you also want the ability to say, oh, we screwed up the data in that column, drop it, we don't need it anymore, but recreate the column with the good data so that none of our existing queries break, right? We don't want this data getting into existing queries, but at the same time, we don't want to rewrite all of those queries to use, profile ID 2 if that was incorrect. So undead columns are a serious problem, and this is something that Iceberg just gets rid of. We track everything by ID, and so you get full schema evolution support. Alter table, rename column, totally works. Now, the next thing that we've done is we've taken that idea of in-place evolution. You shouldn't have to throw away a table or rewrite the entire thing or just deal with, undead columns. You should be able to do the same thing for table layouts. One of the restrictions in Hive was that you could only have one table layout, and it was set at the time that you created the table. So what we would see is users at Netflix that were coming from a different world, the large MPP databases like Vertica or Teradata, they would kind of expect to not have to configure partitioning up front and have that be correct for the next 5 years. 1 second. But that's not the case in Hive. In fact, everything is more difficult in Hive tables. So we would see people making mistakes, forgetting about partitioning, not specifying partition columns when they create tables. And then getting 2 months into production, suddenly having a data volume that requires partitioning and realizing that now not only have they started writing into this table, but everyone downstream has started using it. So they've got to rebuild the table with partitioning, reload the new data into it, split the stream to feed both tables, and then help their customers go write every single query that was accessing that table. And that can take months. Honestly, with a large table, if you're just going from daily to hourly partitioning because your data volume has changed, that is a massive headache. So partition evolution or layout evolution in Iceberg is super simple. It's lazy. You don't have to rewrite data, but you can if you need to. It's a DDL statement, as you can see here, alter table, add partition field, bucket on ID, and boom. The writers, the writes into that table are going to be updated to use that partition column, and it's going to save rewriting all of those queries. So this is a really huge usability improvement. Now, neither of these things is something that you're going to think, these aren't things that you do every single day. But when you need these to be there, it saves you a day or a month worth of time. And so that's super important. And this is one reason why we really wanted to get this right in Iceberg. Next, I was talking on the last slide about layout evolution. Now, layout evolution is just not possible in Hive. You can't change the partitioning of a table because partitioning is exposed to users. When users write queries, they're actually saying, not only, give me this range of timestamps, but give me this range of dates as well. And there are two huge problems with that. So first of all, the person querying the table needs to know about the physical layout of that table and add extra predicates. And this is where we're stealing people's attention, right? Someone needs to think, wait, is this a partition table? Should I add extra, not just predicates to match the data that I want, but predicates for the physical columns that will make this query more efficient? We shouldn't be doing that. So Iceberg hides that. Iceberg keeps track of the relationship between the daily layout of your table and the timestamp column you're partitioned by, and can take your filter on timestamps and bake that down into a predicate on files and use that. We can also then bake that down into a predicate on column ranges in each data file and get super fast queries out of this. Not what we're talking about today, but just want to note that as well. So hidden partitioning is actually really powerful because you don't need every single downstream consumer of a table to understand the physical layout or even what partitioning is. They can just query the table and get good results. We think that in terms of not stealing people's attention to think about concerns in the data format, this one is super important. Hidden partitioning also fixes silent correctness bugs and conversion mistakes and all sorts of things for even people who are very good at building these queries and moving data around. If you accidentally use a dash instead of a slash in your date format, or maybe you use a space in your date format or something like that, those mistakes turn into silent correctness bugs on both the write side and the read side, right? If you're saying here's the format I want to convert this timestamp into a date with, well, that's very sensitive to what format did you use, what delimiters, what time zone were you in when you did that? Did you remember to specify the time zone? All sorts of conversion mistakes. And the same thing is true for the people that are querying that data. If you use the wrong date format, you're just going to get silently incorrect data. That's really, really bad. We really don't know how many people are affected by this, but it's something that you should worry about. And again, that's just stealing your attention. The last thing I'm going to talk about with hidden partitioning is, tying it back into layout evolution. If you want to change your partitioning, but you're actually building predicates on, the date column that you had to derive, well, you can't change that date column into an hour column and expect everything to continue working. So it's really important that we're doing that conversion from timestamps to either dates or hours, depending on how the table's data is laid out. The next thing that Iceberg does that I think is not obvious, but a huge usability improvement is it turns everything into table configuration instead of job configuration. So before, if you wanted to do something like tune your Parquet file settings, which, by the way, we know no one ever does. Say you wanted to set the row group size for your Parquet tables. You would have to go figure out how to plumb that through either Trino or Spark or Hive or whatever you're using, maybe even Pig, that sort of thing. Whatever you're using has a different way of controlling those settings for each write job. And that's not even the right level of granularity, because you might set your general Spark size and write to 3 different tables in a job. Well, that's not the same size for every table. So you're not only making it more difficult to tune these settings, you're getting it wrong because you're applying settings globally to anything that happens inside a job. So we think that table configuration is actually a really important thing here. Now that tables can carry their own configuration, we're moving more and more there. And that allows us to have consistent settings across any engine. So Trino and Spark and Hive should all write the same way when they're writing data to your table. Same thing with Flink. It should respect the Parquet row group size that you decided to use. Not only that, but having a single way of doing this that's respected by every writer to the table means that we can automate table tuning. And this is particularly important because this is clawing back things that users and data engineers have previously had to care about. This makes table tuning settings a data platform problem. How do we figure out for every table the right Parquet row group size, the right compression codec, the right, whatever tuning setting you want? And these are actually data dependent. So the things that you as a data engineer never, ever look at, we can actually do a much better job of reducing the size of your table. So with automated table tuning at Netflix, we actually got some pretty amazing results. Just choosing the right compression codec can reduce the size of your data by 20 to 40%. Choosing the right table sort order, because we're making like clustering and sorting config also part of table metadata. Just choosing that can reduce it by another 40%. There are huge wins in terms of how much data is on disk, and consequently, how much data you actually have to read from the object store when you're querying a table. So there are some pretty impressive gains here from just taking something and saying, data engineers, you guys don't have to worry about that anymore. So that's something that we're thinking about with Iceberg, and a direction that we really want people to move into. We want to be able to automate those things and really bring it back to the platform's responsibility rather than a data engineer's responsibility. Quick shout out to my own company, sorry. It's not called Iceberg, it's called Tabular. My own company, Tabular, that's what Tabular is doing. We're working on ways to automate table tuning, automate different things that you would otherwise do manually. So clustering and sorting and those sorts of things, we're building services that can do that automatically on your tables. Again, so that you guys as data engineers don't have to think about those things. The other usability improvements I'm going to cover are, well, pretty much just the other 2 things that we were doing with Iceberg, disguised as usability improvements. So first of all, call out indexed metadata. So this is really the performance side of things. Iceberg uses indexed metadata to make job planning faster, query execution faster, and basically get you better results in a shorter amount of time. Now, this is not directly a usability thing, but faster iteration, not having to think, well, this is going to take 10 minutes, so I may as well go get coffee. That really does have an impact on the ability to use data. And so that's really one of the aspects of why we're talking about performance. The other aspect of why we're talking about the reliability or atomic transactions is that, once again, reliable updates or being able to automate changes to your table is a really important thing for automation. So what Iceberg does by giving you the ability to reliably update a table, swap 5 files for 1 compacted file or something like that, is, at the highest level, it's stopping manual cleanup if a job fails or has any sort of issue, which should take, a lot of weight off of data engineers' shoulders. If something doesn't work, you're not cleaning things up by restoring objects in S3 and trying to figure out what was the state of this table before we ran this operation that just deleted stuff and then hoped the write would succeed. So that's one aspect of it. But reliability and solving reliability, Iceberg really unlocked this situation where we can use any query engine and use them in parallel. So this is really quite nice. You can use Flink to write data to a table. You can use Spark to maintain it and do maintenance procedures on it. You can write your own data services that operate on data in a table. And we're really moving to a world where you have the flexibility that you want. Really that flexibility I was talking about at the beginning when I talked about using multiple engines or whatever is good for a task. That becomes possible because we're brokering transactions and we have those reliable updates for any table. The last thing here is, like I was talking about on the last slide, we want to be able to automate maintenance. And before, when we didn't trust that we could safely compact data in a table, except at the whole partition level, or we could not do certain things safely, we just neglected maintaining our tables. And that neglect turned into responsibility for data engineers. So we couldn't automate things, so we just said to data engineers, don't write too many small files because there's no way to clean it up. And that's kind of ridiculous. What we ended up saying was, hey, data engineers, you need to care about the layout of files on disk for any given write that you're performing through Spark or any other engine. That means you have to understand how that's happening. That means you have to, look for problems as data volumes change over time. And it just puts an enormous amount of responsibility on data engineers, all because we didn't have reliable transaction semantics to be able to just build something that detects small files and smushes them together. So that is really where we're headed with the Iceberg community, towards that automatic maintenance. We want data engineers to focus on the parts of their job that matter to the organization and to their customers, and not on the things that are performance headaches, because we should be able to automate those things. So in short, what I want to tie this all together with is that we're building tables that work like tables, just SQL tables, straight out of 1992. Schema evolution that is reliable, layout on disk that you don't have to worry about as a data engineer other than configuring it when you create the table, a separation between the logical rows in a table and physically what's on disk so that you don't have to worry about that as you're writing into a table. These are really just things that restore the overall table abstraction that we enjoyed with SQL systems for a really long time. The main thing that we're doing here is we're just applying those older ideas of how to have reliable schema evolution to the open source big data space. And we've seen, at least at Netflix, that was incredibly powerful, again, for just productivity and how data engineers can address problems and not have to carry this mental load of, can I do this in this table? Is this going to break something if I run this command? We need to not have unpleasant surprises, and we need to stop stealing the attention of our data engineers for concerns that should be automated or concerns that just don't even need to register in your minds. So tables that work like tables. That's my main thing. So next, we're going to start and just do a super quick getting started demo, and then move on to questions, because I know that there's probably a lot of like compare Iceberg to X, and how do I, Y questions. So let's do a really quick demo. If you want to follow along, and you already have downloaded like Spark and some things, there's a getting started page at iceberg.apache.org/getting started. This right here is essentially what we're doing. So in 5 lines, because I had to wrap the Spark SQL line, we add the Iceberg runtime jar. Spark will automatically download it from Maven Central, so you don't have to worry about that. In this case, we're using Spark 3, so we use the Spark 3 runtime. We're enabling Iceberg SQL extensions. Those add the new DDL statements that I was talking about, like alter table, add partition field, and a lot of other rich ways to interact with your table. Things like setting the sort order on your table so that when you write from Spark, you get that sort order. And then we're also creating a catalog. So I called this catalog prod, and then I quickly moved on to use test in my demo. But the configuration here, Spark SQL catalog dot whatever, all of those properties configure a catalog. So we're saying use the Iceberg Spark implementation of a catalog. And by the way, that's a Hive catalog. So pull the connection URI from a Hadoop configuration. So that's all you need to get started. There's more information on the website if you want to follow along. But let's move over to a demo. Okay, I'm drawing on stuff, so 1 second. New share. And this is how easy it should be to get running with Iceberg. So I started this Python Spark notebook here. And all this is doing is it's already importing Spark and basically allowing me to get a Spark session set up pretty easily. And what it's doing is it's going to use these settings that I have in sparkdefaults.conf. So if I run this, you can see what my Spark defaults are. I'm setting my default catalog implementation to in-memory because we're going to use a V2 catalog. Again, we're pulling in the O.12 runtime jar. We're actually adding another catalog that we're going to load dynamically. This is the tabular catalog because that's what I happen to use. You can easily use the type equals Hive catalog as well. So this is where we're actually setting up the catalog implementation. I'm just plugging in my own. We're using the Spark catalog implementation that plugs into Spark, Iceberg Spark extensions, and then a couple things to configure my catalog, like a token for interacting with the tabular service. All right, and with that, we then start a Spark session. All right, and what that's going to do is then go, and you can see it's using Ivy to go download everything. I happen to already have this downloaded, and then it starts a Spark session, gives me a nice link to the Spark UI, and we're up and running. So the first thing I'm going to do is use a couple of SQL magics to run, use test.movielens, which is my database with some movie ratings data from the MovieLens project. It's just a free online data set that you can use, and I use it for testing. So now we're using the test catalog and the MovieLens database within that. And if I can then run like show tables and things like that. So as you can see, Iceberg is now integrated with Spark pretty seamlessly. We're using Spark SQL here, and I can even do things like data frame equals spark.read.format iceberg.load test.movielens.movies limit 10. Oh, I'm running another query, so that might take a sec to finish. And then df.show. Oh, yep. it's going to take a little while. So I should not have run that other query. This is basically, let me explain what we're running here in the current cell. So we have a ratings data set that has 3 tables: users, ratings, and users. And movies, sorry. And what we're doing here is we're joining movies and ratings on movie ID. We're grouping by the title, and we're filtering down to titles that have more than 100 ratings. Then we're taking the average of those ratings, and we're ordering by that average rating descending. So what that's going to show us is basically the best movies according to the ratings in the data set that we know about. And this is basically scanning the whole big data set right now. And it's doing so on my laptop, which is why it's moving so slowly. So actually, I'm gonna, since we are moving pretty slowly through demo time, why don't we move it over to questions, and we can just open it up to questions. We'll come back to this if it finishes, sometime soon.
Sure, that's fine. I since you earlier mentioned that there's a lot of questions about compare Iceberg to X and Y, so I probably just gonna go to that question first. I think our friend Andy Fong asked the question. Please offer a high-level comparison between Iceberg and Delta Lake.
Yeah. So there are a couple things to keep in mind here. First of all, I think openness and an open standard and open community is really super important for infrastructure projects like Iceberg. If vendors can't trust that they can use a product and be successful with it, they're not going to integrate. And so we thought it was really important from the get-go that anyone that wants to integrate with Iceberg has a voice in the community and can participate and really have a neutral community where they can all participate in the spec. So we think that is really important for building a successful format. Formats last for 10, 15 years. So we really want this to be something that lasts, and an open community is a huge part of that. The other thing is basically what today's talk was about. The usability focus that Iceberg has is fairly unique compared to Delta Lake and Hoodie. Now, I know Delta Lake has a lot of the same features, so like the merge into and the row level SQL support and things like that. But it really lacks stuff like Schema Evolution. The alternative projects came out of the need to fix transactions, and Iceberg did too. So Iceberg fixes transaction semantics and the reliable updates problem and things like that. The difference is when we were at Netflix, we said, we're doing a lot of work here. We're ripping out basically the bottom layer of all of our processing engines. What else do we need to fix at the same time, right? What else gets us to our goal of productivity for data engineers? And it wasn't just the one, atomic transactions feature that was motivating us. It was that whole breadth of problems. And so I think that Iceberg is more forward-looking because we said, let's break compatibility, let's build it right, let's get these database principles back into the hands of our users because they're going to be more productive in the long run if we do it now. And I think that's really what differentiates Iceberg, the open community and the forward-looking aspect of not just focusing on atomic transactions, but really solving the challenges that take your time, even though that's not like the the single problem that we started with.
Excellent. So I'm going to ask a question from the top now. So after that question, So first one is about your company. How does Tabular make money?
Okay, really quick, I just want to point out that we have the query back, and we can see, everything worked as expected. I'll now answer the question. So Tabular is basically data infrastructure for people that don't have big data infrastructure teams, like Netflix. Iceberg was rolled out at Netflix, and I think we talked about this earlier because we were running the data platform and we were able to do it easily, right? And basically curate that experience and make it possible. Other companies don't have a 20 to 60 person data platform team looking at this stuff. And so that's why we created Tabular. We want to build a SaaS service that is basically Netflix's data platform team for your company and for everyone. So that's how we're planning on making money. We think that there's a lot of use in the Metastore component, the security story, and the things that are around Iceberg. Iceberg is a great at-rest format, but there are a lot of things that are needed to deliver that to production. And we think that Tabular is going to be a great way for you to do that.
Got it. So do you want to finish your demo before I continue the question, or you want to?
Well, it's up to everyone here. Like I can demo things like time travel. I really wanted to see what the group is interested in. We've got time travel, metadata tables. I have a different notebook that's running Flink, so you can see like Flink streaming, that's probably a bit more involved for the time that we have. So whatever people are interested in.
We have a few minutes, and I don't know, the people who's more interested in the question are just the demos. Okay, maybe we can quickly go through the questions, and then if you have time, we can.
Yeah, let's do it.
Okay. So, so the next question is there a built-in version control for schema revolutions? So can you roll it back easily?
Yes, you can. So when you change a schema, we create a new version of the schema on the table, and you can change the pointer back to the older version of the schema. You're effectively, deleting some data, and you could do the exact same thing through DDL statements. So it's probably easier just to do it drop the column that you added, rename back to the original and things like that, because you can actually do that in DDL. But if you wanted to, you could. The one thing that you cannot do is roll back the schema IDs. So we keep a high watermark of schema IDs that have been assigned, field IDs within a schema. And we do that so that we don't ever use the same ID twice, because if you use an ID, write data into the table, roll back, and then reassign that ID, you're going to mix data. So we've handled that case, and we don't recommend doing that. Got
it. So next one is what is the easiest way to turn the Panda data frames into an Iceberg table?
Well, so what I was just demoing in a notebook was basically a PySpark environment. So, start PySpark, do your from pandas to get a Spark data frame, and then just write that directly into an Iceberg table using, create table as select, or, some plan that bakes down to that. You can use the write to API in Spark to do it.
So the next one is, what is the process of migrating our Parquet table to Iceberg?
Good question. So Iceberg, in addition to the DDL statements that I was talking about that allow you to set the write order and some other aspects of table metadata, we have stored procedures. And so we've exposed all of those operations, so table maintenance things, and just a second, thank you. Sorry, my daughter. We've exposed table maintenance and import operations through stored procedures. In addition, we also have a direct API that you can call. That allows you to basically point to an existing Parquet table and say, snapshot this. So build metadata around it and let me play with that, but don't actually change the original table. And then you can also migrate a table, which will replace the existing table with the new one.
Got it. Okay,
so documented on the Iceberg site. Sorry to interrupt.
So next question is, what does Netflix use Iceberg for?
Well, so Netflix is using Iceberg for a huge number of things. So like all of the streaming data that's coming from like telemetry devices, so runtime systems have telemetry data coming off of them as metrics. So all of the metrics, all of the information coming from services like logged events, basically anything falling through Kafka goes into Iceberg tables. From there, we also use it for ETL jobs. So we ETL from one table to another, and a lot of the pipelines are using Iceberg. Almost all of the new ones are using Iceberg these days. We also have projects that do things like expose certain log events to customer service really, really quickly through Presto. That's using an Iceberg table because the metadata indexing is the only thing that allows us quick enough access to really support like a customer service dashboard. And then, we were using an in-memory database, but we were able to replace it with a cheaper option. And then we also have a log project. So like logs from systems get aggregated, converted to Parquet, and then committed to Iceberg tables again, so that they can be served using Trino or Presto.
Cool.
So a huge variety of things. In fact, like a lot of things that we didn't even see in the beginning getting moved over to Iceberg.
I see. So the other questions coming says, when you speak about automation, are you referring machine learning process?
No, I'm just talking about basically data services, right? Having a service that looks at your tables and says, hey, you just committed 1,000 tiny files that can be compacted together. Bring down the size of your metadata, bring down the processing cost of hundreds or thousands of round trips to S3, like that sort of thing, where we're looking at what do data engineers have to pay attention to, and can we just take care of that automatically? And we're doing that in two ways, right? A service that goes and compacts that data into larger files, definitely doing that, because that's something that Flink needs. Flink, you want fast commits and very parallel to keep up with your data set. So you're going to have cases where you need to do that compaction. On the other hand, if you're using like a batch process, like a Spark, what we're doing is communicating the configuration of the table back into the Spark plan. So Spark itself can minimize the number of files that it writes. By knowing the desired sort order and partitioning of the table, we can feed that information back into Spark. And this is something that's going to come out in our Spark 3.2 support. Be able to control the sort order that Spark uses to prepare the data for that write. And so that we write it the correct way the first time without taking a data engineer's time to think, okay, how do I want to order this data when I put it in? And also so that we can automatically tune it.
Yeah, that's super cool. That's super cool. Okay,
it's
the next one.
A long time, because we have had to make significant improvements to the Spark engine.
I see. So the next question is that when you say automation maintenance, how does that something like compaction work under the table in Iceberg? Does that happen at a write? Is there a background process?
So yeah, we want it to be at write time, but we don't want to take up data engineers' time with it. So that's why we want declarative, like, here's how my table should be ordered, and then feed that data back into the query engine so that it can write the data correctly the first time. But we also want background services, because if you need to, ratchet up your the number of workers and commit small files in order to get data available, to downstream consumers on time, you should be able to do that. But then we should also not take a data engineer's time to schedule something that goes and reads that data and rewrites it in the right way, right? We don't need a person to do that compaction.
Totally, totally. And there's one last question, and then we'll say the more demos. But the other one is that if I'm stuck at Spark2.x, is the delete row function not available?
In Spark 2.4, deletes work as long as they're aligned with partition boundaries, but the row level deletes are only in Spark 3 and beyond. In fact, SQL in general is only supported in Spark 3 and beyond because the new data source v2 API just wasn't present in the Spark 2.4 line.
Right. Upgrade to Spark 3.
Yeah, I know that's a big ask.
Yeah.
I built the Spark distributions at Netflix for a long time, and so I know it's painful to upgrade, but it is definitely worth upgrading to Spark 3.
Yeah, I think we just finished my team just finished that. It was a major effort. It's because it's not only just Spark. There's also Scala versions and there's a Metastore versions. So both have to change. So that was a big, big effort. Okay, there's Andy asking another question. On the flip side of the small file compaction, does Iceberg help with data skew? And example, partition that goes too large?
Yeah, so data skew, like we've seen cases where skew causes partitioning to just act really strangely. Like you want the benefit of partitioning, but your data is skewed, and so you have some partitions that are gigantic and some partitions that are tiny. And how do you deal with that? What we've had success with in Iceberg is removing the partition layer from using that column. So a good concrete example is like, country code. We have traffic coming in from all over the world, like Netflix at least has most subscribers in the US, or a lot of subscribers in the US. It might not be most anymore. US was a huge country code. Well, what you do is you just remove that layer of partitioning and still cluster the data. So sort by that column, sort by country code, so that a set of files has the US data, a set of files has other data, and then we use the min-max stats at the column level, right? And this is something that I think only Iceberg is doing, the min-max stats at the column level to filter out all the files that are not the country that you're looking for. So that gives you basically an extra level of filtering that you can use if it doesn't align with partitioning.
I see. That's a very cool feature.
Yeah, that actually, so before Iceberg had implemented vectorization in Spark, we got basically on par performance from just skipping more data. So like if you had to read all the data, it was slower until we implemented vectorization. But overall, we think that we were better off just because we were skipping far more data in Spark.
Cool. And there's one question from David. Is Iceberg useful when all the data fits on one server?
Fits on what?
One server. I'm not quite sure.
So yeah, that's an interesting question. Like Iceberg's ideal use case is, like it was intended to scale up to tables in the tens or hundreds of petabytes. So like it works for that. It does scale down effectively though, right? Like Iceberg basically provides you a library for partitioning your data, working with it in different engines, and keeping track of metadata across a lot of files. So if keeping a large data set on a single machine and accessing it efficiently is something that you're interested in doing with the tools that support Iceberg, absolutely go do that. I mean, that's how I test Iceberg all the time. I just crunch some things on my local desktop. So it works great.
So we are 6:06, probably already past the time. I'm not quite sure we'll have time for more demos, even though.
Yeah, I should probably get going.
Yeah.
My daughter walking in is definitely a sign that, is late here, but thank you so much for having me. It's been a lot of fun to talk with you guys. I hope everyone found it useful and enjoyed it.
Yeah, it's a pleasure of mine. Thank you, Ryan, for the great talks, and everybody's see how useful the Iceberg. We have great deep interest from the community about this project. Thank you again for coming to give a talk.
Anytime. I'll look forward to more. Maybe we can get into more internals or more in depth next time. So
definitely.
Thank you, everyone. Have a great night.
Thank you. Bye.
Thank you, everybody else. See you next time. Okay, bye-bye.